Hello everyone, I'm Ali Ghafal-Bashir, and today I'm going to present my research project, Congestion Reduction via Personalized Incentives, that I've been doing with my advisor, Professor Mason Razavian, and also Professor Majid Desuki. First, let me go through the motivation and background. We know that traffic congestion cost in US just in 2019 was $88 billion. And we know that longer traffic can worsen the air quality. So 3 different categories of strategies have been used to solve traffic congestion based on Cambridge Systematics report. The first category is adding more capacity. So we want to build more transportation infrastructures, such as adding more lanes. But the problem is that it is costly. And at the same time, based on VMT, we know that it does not necessarily improve our traffic congestion. The second category is transportation system management and operation, or TSM, in which instead of focusing on building infrastructures, we want to use our infrastructures efficiently. An example is reversible lanes. We have it actually in Golden Gate Bridge of San Francisco. Another example is dynamic traffic signals. And it's less costly in comparison with the first category of solutions, but still we cannot only rely on this category. The third group of solutions is demand management, in which instead of focusing on infrastructures, here we want to focus on changing the behavior of the people. And also this research project is also providing a solution from this category. One of the examples from demand management is road pricing policy. For instance, distance-based charges that for each mile driver should pay some money, or cordon-based cordon areas that we have that you should pay some money to enter a region. But although in theory and some cases it has worked, the problem is that we have equity barriers. The distribution of wealth in society between people is not same, and sometimes some people cannot afford paying for these charges. So to solve this issue, another way of looking at the solution is rewarding policy or positive incentives that successfully have been used in some projects. The first one that I want to talk about are the first one is 3 projects that we had in Netherlands, and it was trying to motivate people to avoid during rush hours. So the first project was in 2006, and it was a scientific project that alternative options for drivers was changing the departure time, changing the travel mode, or just teleworking, staying at home and work. And drivers, actually, these people could earn 3 or 7 euros. And the second and third projects were real problems that 2 bridges were being maintained, and they wanted to avoid making congestion, avoid creating traffic congestion during the rush hours on these bridges. So they provided options of changing the departure time, changing the travel mode, and also being able to change the destination and route. And they were all based on receiving monetary incentives, and they were all successful. The second one that I want to talk about is Capri project of Stanford that was between 2012 and 2014. And drivers were motivated to avoid driving during the rush hours, and they should avoid rush hours and drive during the off-peak hours. They could also bike and walk to their work, and they could earn gain points that could be redeemed for money. Like 100 points could be redeemed for $1 that it was worth of 1 week of driving during the off-peak hours. And also another option was playing a game that could the people could win between $1 to $50. And it was also another example of incentivizing that was actually successful. Also, this research project is focusing on rewarding policy. In this research project, we want to offer monetary incentives to change the routing decision of drivers to take alternative routes. Any questions so far? Okay, let me go through the incentive offering process and explain to you what are some differences that we have with previous projects. So the first of all, our offering process is personalized. Let me explain it in more details with a toy example. So personalized means that for different individuals, we have different behaviors. Here we have two individuals. They are going from home to their office at same time of the day. So origin O and destination D is the same for both of them. The first individual maybe is in rush and doesn't even accept $4 for the route that we have offered. But the second person maybe doesn't have an urgent job. And this person accepts half of this money that we offered to first person, which was $4. And this person, he or she accepts $2. And now we can see the differences between individuals when it comes to same scenarios. Also, another thing that we should take care of is that our offering process should be dynamic. What we mean is that for different times, same individual here in this example can have different behaviors. Same individual at 7 a.m. is in rush maybe and doesn't accept even $4. But at 4:30 p.m. when this individual is going from home to office, same OD as the previous one, accepts $2, which is half of the previous scenario, which was $4. Also, for different routes, the behavior of accepting offers is different. Same individual at same time for same OD may reject $3 for one route, but accept $3 for another route. Also, another thing that we should take care of is avoiding creating new congestion. Here I have an example of a simple network. I have 4 points A, B, C, D. My origin O is point A, my destination is point D, and some drivers are going from point A to point D. The red links here shows congested roads and blue ones shows roads that have a free flow traffic. So here we can see that we need to solve these two congestions. In scenario A, we can do it by deviating drivers from road A to B and road C to D. Here you can see that for D, the number of drivers became 30. And also here 4D became 30. So maybe the capacity was, we can say that it was 35 and it became below the capacity of the road and congestion is solved. But in scenario B, we again have deviated the drivers from their route, some of the drivers, but we can see that not only the congestion of link C to D is not solved, but also another link that wasn't congested before, A to C, now is congested. So we have created new congestion, and it's something that we should avoid. Any questions so far? Okay, now let me go through the incentivizing process and give you a high-level idea of our this process, and after that we can go through a detailed explanation. So in high-level idea, the high-level idea is that first drivers share their traffic data and their preferences, and it will be sent to our central planner. In the next step, step 2, what happens is that, I'm sorry, excuse me. We offer incentives, the central planner offer incentives, and these offers will be sent back to drivers so they can make decision. So let's have a more detailed explanation of these two steps. First, users send OD information. It can be via a smartphone app. The server receives user data and traffic data, and based on it, makes traffic prediction and find the possible routes for the driver. In the next step, we offer incentives to individual drivers that can be monetary incentives, for instance, $5. It can be coffee coupon like Starbucks coupons, or it can be some grocery coupons, or it can be tax reduction. Next, the users receives these options. Each individual receives his or her options and makes decisions. Any question about incentivizing process?
I think just a quick question. Is this something that can be integrated with Uber and Lyft, or is it something that has to be like what kind of agency would be able to run this kind of process?
So when it comes to having Uber and Lyft, they should have some like budget. They should know how they want to offer incentives. But for this project, we assume that there is an agent, like there's an agency that has received, for instance, money from government and is offering incentives to drivers that send their information. But it can be also so some packages. We can offer some packages to Uber and Lyft to give to their drivers, so they can change their decision of their own drivers. But at the same time, we should understand that the passengers should accept it, right? That's the part that we should take care of. But here, drivers are making decision for their own path, for their own route.
Okay, thank you.
Let me also jump in. This is Mason. This is a very good question. This work is for providing incentives to individual drivers, but we currently having a follow-up work that we are working on, studying the offers incentives to like platforms like Uber that you mentioned. But this work is currently for the individual. Thank you.
Alan has a question. Alan, would you like to ask your question?
Thank you. And it's from a slide or two before. You made a statement that you felt that VMT unfairly impacts lower income drivers. And I guess my concern is that I think they actually save money. Lower income usually drive older, more gas consuming cars, and assuming VMT replaces excise taxes, it could very well be that they benefit as a result of VMT.
Okay, so in terms of VMT, it could be beneficial. I agree. Okay.
And Jesse has a comment. Jesse, would you like to ask your question or make your comment? No? Ali, if you look in the Q&A, there's a comment from Jesse.
Let's see, for dollar incentive ways, carpool is one possible agent. So Waze carpool, do you mean the app Waze? Because I have not seen this option, Waze carpool. So, okay, it's, I think I can check it later because I have not seen Waze carpool before.
Check it later, no need to discuss it now.
Okay, sure, yeah. If you can help me to know what's Waze carpool.
Will do.
I'm sorry?
We can follow up later.
Okay, sure. Okay. I have another question. Because we measure induced travel on users that normally.
Yeah. And Ali, let's read the question because people might not see this. Ali's looking at a question from Josh that says, where in the process would you measure induced travel, i.e. users that normally take an alternate route but then shift to the newly decongested route?
Oh, okay. So we assume in this project that when you accept a route, you do not change your path. So you follow the route. We have this assumption. And for the measuring induced travel, when we know so it's actually probabilistic. So when we are making offers, we know with some probability driver will accept it or accept the offer or will reject it. And based on this probability, we find the induced travel time. So somehow we have expected travel time.
So let me like also add two comments, like about the comment about the cars and the individual cars. They have different profile in terms of their carbon emission footprint. The one thing that you can consider is when you do individualize incentives, you can provide, for example, you can consider that into your calculation, your model. Ali will get to that. So,
okay, so we will have it in the model part. Yes. Okay. Let me, if you want, I can go to the model. It will be in the next slides, and we can see it later in the model that we use carbon footprint to see what happens when we offer an incentive to a driver, and what's the decrease of carbon emission. Okay. Any other question or? Okay, let me, so in the final step in incentivizing process, the user makes decision. Now let me go through the modeling part. What should be our objective and goal? First, it can be minimizing incentivizing costs, or it can be maximizing a utility of the driver's travel time, or it can be minimizing carbon emission footprint. A simple formulation can be minimizing cost of offering incentives, subject to volume being less than or equal to the capacity of the links. And as a driver's responses are random variables and are not deterministic, instead of deterministic volume, here we have random volumes, and we should consider expected volume. And another thing is that we can also consider expected volume plus the standard deviation. But although it's an integer linear programming problem and we can use off-the-shelf solvers, it has some disadvantages. So first of all, it's not, the question is that, is it fair? Because we are only focusing on minimizing the budget that we are spending. And secondly, it assumes feasibility. So it assumes that there is a routing strategy that actually satisfies the feasibility of that is below the capacity of the links. So another way of looking at this model is that instead of minimizing cost of offering incentives, we can maximize the utility of drivers' travel time to take care of the fairness problem. So here we are trying to make sure that we are maximizing utility of drivers' travel time. And the second difference with the first model is that here we had minimization of cost of offering incentives. We brought it into our constraint. So cost of offering incentives should be less than or equal to a specific budget that we have. But still, the major limiting assumption that here we have is that we are operating below the system capacity, and we are considering feasibility. So any question for the first two models? Okay, and now let me go to the congested network. So let's assume that we want to maximize the utility of the system that depends on speed, volume, and routing. And we use term expected volume because, as we discussed before, it's a random value and it's not deterministic. So we just say expected volume. Something that we know is that speed indirectly depends on expected volume based on BPR function from study 3. So if we have the expected volume, we can compute the speed. But now the question is that how can we estimate the expected volume? To estimate the expected volume, we need to have the routing information of drivers, and we can get the expected volume from routing information of drivers by using matrix R from study 2. This matrix includes the probability of being at a link at a specific time if you have started driving at a point. So you have the routing information of drivers. By using this matrix R, you can get the expected volume. But to get the routing information of drivers, what we need is that we need to know what incentives have been offered. Based on the offered incentives, by using probability matrix P that we have borrowed from study 1, we can get the routing information of our drivers. This probability matrix includes the probability that the driver will accept a route when we have offered some incentives for it. Now let me go from end to start that I had. So first we have offered incentives. By using matrix P, we get the routing information of drivers. Now that we have routing information, by using matrix R, we get the expected volume. And by expected volume, we get the speed. So now I have the utility and I want to maximize it. So now let me make it more concrete. We want to use the total carbon emission as the objective in this model. What we have here is minimization of total carbon emission. That here what you see, f of c is carbon emission function. It gets actually speed, but based on BPR function, we change the volume at link L at time t to speed, and after that speed will be used in our carbon emission function, and the output will be the emission per gram per kilometer. We multiply it by the length of link L to get the total gram. So it's the carbon emission for one individual at link L at time t. And after that, we multiply it with the number of drivers at that link at that time. So we get the emission, carbon emission for that link for all the drivers. Next, we sum it up for all the times and for all the links. Our first constraint is estimated volume. Here we use study 1 and 2 to get matrix R and P, and we can get the estimation of our volume based on the process that we had from S using P and after that using R to get the volume. The next constraint is about incentivizing incentivizing each driver only with one incentive. That this one incentive can be even $0, so it means no incentive. But at the same time, we can have multiple incentives for our drivers, and this model can be changed to also consider multiple incentives for each individual. The next constraint is our budget constraint, and we say that the constraint that we have, the budget that we have paid should be less than or equal to omega, which is our total budget. And the next constraint wants to make sure that the model is aware of the number of drivers per ODs. So if 5 drivers are going from O to D, we shouldn't consider 10 drivers. We want to make sure that this constraint is giving this information to our model. And then the last constraint is for our variables that are 0 and 1. It's 0 when we do not offer an incentive, and it's 1 when we offer the incentive. The good thing about this model is that it's a modular design. So it can be changed. These red boxes that we have can be changed if we need it. Here we have used BPR function, but you can use your own function that you prefer that can change the expected volume to speed. So for instance, for probability matrix P, if you have data of preferences of drivers, you can use preference learning and learn the probability of acceptance of an incentive by an individual. And in the another way of learning these modules is using just parameterizing them by neural network and learn them. But still the question is that how should we solve it? because it's large scale and it's challenging. Any questions for the congested network model?
I just had one clarification, please. So
Sure.
is this part of the analysis, the graph that you're showing there, showing here part of like only the passengers which take those incentives? How does it integrate with the overall congestion problem or the overall traffic routing problem?
So here, as you can see, the objective is minimizing the carbon emissions. So the goal here is that you can minimize the total carbon emission, but still this can be changed also because it's a utility of the system. You can minimize it, for example, for total travel time. And based on, for example, your concern, by minimizing this objective function, you reduce the traffic congestion. For example, you can use even total travel time here. And these constraints wants to make sure that you're satisfying all the, for example, you're satisfying the number of drivers that are going from one point to another point, like this constraint. But the objective function is taking care of that part.
So if I understand you correctly, it is the constraints which are coming from the incentives part, and rest of the problem remains the same. Like the overall objective function is the main problem that is being solved, and the constraints are coming from the way we want incentives to work.
So when you want to here, as you can see, you have v hat that is in the first constraint. So this v hat that is being used in your objective function is actually depending on matrix S. This matrix S shows what incentives we have offered. That's where we impact the objective function. But when you want to minimize this total carbon emission, at the same time, you are changing your incentives in matrix S, because when you want to change v hat in objective function, you depend on your variable matrix S. This is the matrix that shows which incentives we have offered and which incentives we have not offered to driver.
Okay, we can follow up later. Please continue with your talk. Thank you so much.
No problem. So an efficient algorithm that we can use here, first of all, let me go through the details of the function f that I have. It's the carbon emission function. The input is the delta, which is the speed. And we have borrowed this function from study 4. And the input is the speed that we have, what we have volume. To get the speed, we use BPR function. It's actually in rewritten format of the BPR function. It's L is the length of the link, T0 is the free flow travel time of the link, and W is the capacity of the link. We learn T0 and W by using gradient descent and the data that we have, and L is just the length of the link. And when you know the volume of the link, you can get the speed. And after that, you put it in the carbon emission function, and you get your carbon footprint. So to solve this, first of all, this model has binary variables. What we need to do first, what we do first is that we want to relax the last constraint to have a convex optimization problem. But still, how should we solve this problem? It's our question. We can use first order methods, and we can use first order methods or off-the-shelf solvers such as CVX and Groby, but it is still challenging due to massive scale of the problem. And the question is that can we use distributed computation or edge computation? In edge computation, actually, what we want to do is that we want to exploit the individual processing power of drivers' smartphones. And it is also our question that can we utilize the processing power of our drivers' smartphones? To do so, we use alternating direction method of multipliers or ADMM to do the distributed computation. So let me briefly explain our ADMM, give you a background. So we want to solve linearly constraint optimization problem in this form that objective function is separable in variables W and Z. Where to write it as an unconstrained problem, we have this augmented Lagrangian function. And to solve this, we use augmented updated rules that sequentially we update our variables. And the efficient algorithm that we have, first of all, we need to relax and reformulate our problem. Here you can see that we have added some variables, and at the same time, this matrix H is, instead of being binary here, we have interval of 0 and 1. And after that, we have ADMM algorithm. And the update rule of gamma of L and T can be done in parallel. So different, and also different columns of our variables W, S, and H can be updated in parallel via H computation. And this algorithm can find an epsilon solution of the, find an epsilon solution in order of 1 over epsilon iterations. And as we have seen, we have here a relaxed formulation, but we want to go to the original one, and we should have binary variables. So one of the ways is using ADMM-Q algorithm. Any questions so far? So in the next part, I want to go through the numerical experiments. Okay, first, in our numerical experiments, let me explain to you our network construction process and the data that we have used. So the question is that how do we construct a network? The data that we have is the data of sensors. So in this figure, you see blue points that are our sensors. And first, we choose our OD points. These OD points are our intersections. But still, we need to have a graph to solve our model. So we create a graph based on this data. Our OD points will be our nodes of the graph, and the OD points that are connected with a road will be connected in the graph with a link. And we have 2 directions because we can go from point 1 to point 2, and from point 2 we can go back to point 1. And each link has speed and volume data that is coming from taking average of the speed and volume data of the sensors on that link. To estimate the OD for our drivers, what we do is that, first of all, we do not have access to prior OD as works like 1 to 4 need. And we have a large scale problem that needs some prior work that cannot really scale. So we have used work 5 that takes the graph of the network and takes speed and volume and does the OD estimation. And the data that we have used is coming from ADMS, Archive Data Management System at USC, that is recording real-time traffic data such as volume and speed by collecting it by loop sensors. And it has a highway data for every 30 seconds, and it has also a data of arterial roads for every 1 minute. And the region that we considered is Los Angeles. And the reason that we have chosen this region is we have available detailed data, and this region includes both heavy and light traffic. And the date is for this data is March, April, and May 2018. We have selected these 3 months from 2018, and we only considered business days. And the features we used were speed and volume. Any question for network construction and data? Okay, now let me go through the first results that we have for a small region. This small region is actually the USC neighborhood that these OD points, the red points are our OD points and the blue dots are our sensors. And this data only, for this experiment only, we included arterial roads. The set of incentives that we considered for our drivers were $0, $1, $2, $5, $10, and $1,000. And we were offering only one of them for a route to each driver. And here you can see the number of incoming drivers between 5 to 9 a.m. that we have chosen 7 to 8, which was the peak of the traffic. And we have checked budget of $1,000 and $10,000. The reduction in carbon emission for $1,000 is 4%, and reduction in carbon emission for $10,000 is almost 18%. So 10 times of budget gives you almost 4 times of carbon reduction. And Also, the percentage of drivers to whom we offered incentives when you have larger budget increases. Here you can see from 9%, we have 43% in $10,000, and the average of the incentive amount goes from 1.5 to 3. Any question for the first experiment for our small region?
I have a question.
Sure.
I actually have two questions. The first question is, did you, let's see, how do I put this? You said earlier that you could offer incentives including zeros.
True.
So is this the percentage of people who were offered incentives including zero? Or is this the percentage of that were included, that were offered a non-zero incentive?
Good question. Actually, this percentage is for positive incentives. It's not
Okay.
including zero. So if you have 8.94%, it means that these people have received $1, $2, $5, $10, or $1,000, and the rest of 91% have received no positive incentives.
Okay, the second question is, you must have a utility function in here somewhere.
So here, if this is coming from the second model that we were minimizing the total travel, that we were minimizing utility of the driver's travel time. So the utility function was total travel time for our drivers.
Right, but we have a probability of them taking an incentive or not, and that has to be based on somebody's value of time, right?
So the probability of accepting an offer is coming from one of the studies that I had in previous slides. Let me, if I
Okay,
can find it. So it's coming from study 1. This is the probability matrix that I was talking about. This probability matrix includes the probability that a driver accepts an offer. This study has used real data to compute get a simple linear regression model that gets features and gives you the probability that driver accepts the offer.
okay,
The features that we considered were travel time of the driver and the amount of incentive. These two features were used to get the probability of acceptance. Yes.
So let me also jump in. So the utility is basically the expected value. So there is a probabilistic model, expected value of total.
okay.
Yeah.
Thank you.
Thank you. That's very good.
Any other question for the first experiment?
Can you just give us a little bit idea about how many drivers, like this gives percentage, but how many, what was the sample size like?
So you mean the number of drivers that I had for 7 to 8 a.m.?
Yes, yes.
So in this plot, we have interval of 15 minutes. So from 7 to 8, I can almost say that 8,000 drivers were incentivized.
Okay, and is there like some reason for focusing on this time only, or you do it for other times as well and you're reporting for this time frame?
So we had in our report, we had for 6 to 9 a.m., but the reason I've chosen it because it's the peak hour here in this region.
Okay, thank you so much. Thanks.
No problem. Any other question for experiment 1? Okay, so to consider a larger region, we also included a good portion of our Los Angeles County. This experiment is for only highways. The previous one, we were considering arterial roads for a small region, but here we consider highways, and the red points are our ODs, and blue dots again show our sensors. And again, the set of incentives that we have is similar to the previous example. And the budget is also 1 and 10K. And we can see that carbon reduction for budget of $1,000 is 0.7%, and for $10,000 is 5.7%. And same rule for the percentage of drivers happens in experiment 2, because you can see that when you increase the budget, the percentage of drivers that receive incentive increases, and average of the incentive is also increasing when you increase the budget. And the reason that I have chosen 7 to 8 a.m. is that, first of all, I wanted to be consistent with the previous experiment, and also here I have the peak. You can see that at 7 to 8, I almost have half of the peak here, and we have actually 6 to 9 a.m. in the report. If you want to check it later, the results for 6 to 7 and 8 to 9 is also available in the report. So we can see that here the reduction of carbon is again increasing when the budget increases. And the number of drivers are actually larger in comparison with the previous experiment, because we are considering larger region. Any questions for second experiment?
And are these incentives for all of the options that you described? So we could ask someone to travel at a different time. We can ask someone to travel at a different route, etc.
So yeah, actually, I have brought it in the future work that we can consider different travel modes. But here we only offer incentives for different routes that is
Okay.
available at right now.
Okay.
But it's, yeah, it's something that we can use, yeah, later. Yeah. Any other questions? Okay, so let me have my conclusion for this presentation. So we have used offering personalized incentives to drivers to reduce the congestion. We provided efficient algorithms to solve the problem in larger scale, and we are utilizing the computational power of individual smartphones by distributed algorithm. The code is available. You can scan this QR code to go to the link to download the code. Unfortunately, the data is not available because it's not public data, but then later, if you need, you can ask for synthetic data that randomly have been generated, so you can see what's the format. And for the future work, we can consider different travel modes, such as public transportation, carpooling, and biking in the options. We can utilize preference learning, as I explained before, to learn the driver's acceptance probability. And more features such as income value and gender in computation of driver's acceptance probability can be used. What we have used is the travel time and the amount of money, but we can consider like income value or the gender of the driver. And implementation analysis of the algorithm can also happen in the real world. And we can combine data of highways and arterial ways, which will give us a more complex network. Thank you so much. So
Okay, I think we say thank you very much. And now we have time for more questions.
Would there be scope of identifying more congested areas where more incentives can be offered, or is this, I mean, does that take into account, is that information taken into account in the present experiment, or was it more about the timings when traffic is at the peak?
So actually, as I explained before, we have the interval of 6 to 9 a.m. in our report. So 7 to 8 is the peak hour, but we can somehow say that 6 to 7 and 8 to 9 can be considered as the combination of light traffic and heavy traffic. But when it's the light traffic, assignments, is not challenging. That the problem comes when we have a congested network. And that's why we choose 7 to 8 a.m.
So I think I'm asking with regards to, like, there are certain timings, like when people are returning from work, that are normally congested, but there are certain parts of the city which are congested because of the, like, the geography of that area. So is that kind of taken into account in this work, or is it possible to take that into account, or it's more like just the traffic flows that are being considered?
What you are referring, as I understand, is we want to know what times individuals are, for example, going to their home from their office, taking into account that information.
No, so I think the idea that I'm kind of getting around to is that if there are some locations where we cannot really change the traffic, because like we can't change the congestion because it is easier to get congested there, the roads are narrow or something like that, then it makes sense to concentrate the offers in locations where, like, there is a possibility of rerouting and possibility of reducing congestion through those kind of incentives. Like, is there a bifurcation of the roads on which we can offer incentives with regards to, like, how they are in general for traffic control?
So when you have a region that is congested and you don't have a chance to decrease the total travel time, so the minimization doesn't happen there because you don't have a chance. So the focus of assigning these incentives will be on the people that are in some regions that we can actually decrease their total travel time.
So the algorithm is already taking care of that. Like, that is how it is optimizing in the first place.
So it tries to push the total travel time smaller as much as possible to so focuses on the parts that we have this chance to decrease the total travel time more.
So let me also add a few comments about this question. So that's a very good comment. That's true that you may not be able to fix some part of the congestion, but we are not explicitly doing it, but we are implicitly considering where to put the incentives because we have a utility function. So if we do not gain any utility on investing in a certain part or certain area, then we do not implicitly, we are not offering any incentives to drivers there. So it's implicitly we are considering that, the algorithm itself, because we are maximizing the utility. But that should take care of that. If our utility is defined correctly, then that should take care of which part or which areas we focus on.
Yeah, I think that's what the algorithm is taking care of, that, like in
yes,
some
exactly.
implicit way. Yeah. Okay.
Exactly.
So I have a little bit more of a philosophical question that your research brings up. And that is that I can imagine a world where one extreme is that there is no congestion on the network. So there is no need for incentives because it doesn't matter if anybody moves a route, moves their route or not. We're already at a free flow and everybody's travel time is minimized anyway, right? You could then think of the other extreme, which is when the system is completely full. And again, it doesn't matter because there's nowhere else anybody can go to make the routes any better. So is there kind of a sweet spot here that, is this something that we really want to look at for places that have, a lot of congestion, but still have room on the system? Do you see what I'm saying? That, there may be kind of types of areas where.
Exactly. That's I think that exactly, you want to have some diversity at least in terms of road congestions in that area. If you look at, for example, experiment 1 versus experiment 2, in experiment 1, you have a lot of different routing options and you gain more by offering incentives.
Exactly.
Because when experiment 2, which is more highways, all of them, and because they're like all highways, they're almost all congested.
Mm-hmm.
So you don't gain a lot by offering incentives. So you don't want to be in either of these two extremes. You don't want to be in free flow. You don't want to be also like in a very congested area, or you don't have any other options. So what we observe is that if you have diversity in congestion, then that helps in the areas that, and that's intuitive. So you want to have other options to assign. Otherwise, there is no point of offering.
Right.
Exactly.
I'd
I
like to add a quick comment. First, Jen is a great optimist to consider the possibility of no congestion anywhere on the network. But
It was a theoretical thing.
hope springs eternal. But focusing for just one moment on the very small piece of this about paying people to carpool, just want to make sure you're aware that there was a recent paper by the Mineta Transportation Institute on exactly this topic. I can send you that paper or a link to that paper. So just FYI.
Okay.
I would
Thank you.
appreciate it.
We really
Yes.
appreciate it. We cite some of the relevant works in our report and and we compare it, but we would appreciate it if you have like other works. We would really appreciate it if you can share it with us.
I think I had just one more question. I think the title talks about personalized incentives, and I'm just curious as to what kind of driver information or passenger information can be incorporated to, like, customize the incentives offered to the driver. So maybe like I'm just kind of like, if you can show me on the model where that part is coming in.
So you had a probability matrix. This probability matrix consists of probability of acceptance of incentives by our individuals. So each individual has its own column in this matrix. So column of each individual can be different. That's the point. The probability for each individual for same routes can be different. When you, for example, take into account the gender of that person, the salary of that person, and other features that are personalized.
So the reference one that Ali is setting here, we use the model there. But in my opinion, the best is to use, for example, for this system to use preference learning. If you have the budget, we would run an experiment and learn it on the fly, use preference learning from computer science to learn what is the preference of different individuals and personalize it. But this study is actually a great study. They study the impact of offering incentives and the probability of accepting it by different individuals and their different attributes, ranging from what time of the day they are going, how far they're traveling, what's their commute time, what's, for example, their education, all of it they consider into their model and they come up with that. And they saw that there are correlations with different factors of the individual. And we use their model in our model. And for modeling the probability matrix P, which is the probability of accepting the acceptance of the offered incentives, we use the model developed in work one.
Mm-hmm. No, I think this is very interesting how this can be done. I'm just wondering if this is something which is already implemented, like there is something which is already going on in Los Angeles about this, or is it still something that's more of a theoretical?
So now we model it. So we haven't implemented that yet. Okay. I know that there are some efforts implementing in general. I know at least, for example, one undergraduate at USC, they wanted to they wanted to have a startup on this idea. But what we did is that we evaluated the best that we could using the real data that we have. So that's what we did, the model, to see the potential of them.
I'm just wondering why Uber would not want to do this experiment. I mean, I think if they can do it, then they would be well positioned to do something like this. Maybe like Uber, Lyft, like any of these, instead of a central agency.
Well, there's another piece of this that was early on in the slides that I think we always have to keep in mind. And that's that, as far as I understand, and tell me, Ari and Mizam if I'm wrong, the assumption here is there's the equivalent of a system manager. So there is some source that knows everything that needs to be known. And then once the driver accepts an incentive, that's what the driver does. So when you get out in the real world, you don't have the system manager. So it's a big leap to take these kinds of strategies and try to implement them in the real world.
That's correct. But at the same time, if I have, for example, an app, or if that offers individual incentives, if you have an app that I have access to the GPS, even right now on Google Maps, they have access to GPS, they have routing information. So they are in the position, with an app, you are in the position of offering incentives. So real time, which is personalized to the individuals. You can personalize it because it's connected to the cell phone, which is connected to a person. We are also in the position of tracking everything real time with an app. But you're right that we are assuming that traffic plan, well, a centralized processor or central planner right now. But it could be resolved, for example, if there is an app that is offering incentives. And there are some apps right now. They do offer incentives, but they are not considering, they're not real-time, online, and personalized. They are not that.
Well, thank you for joining us today, and we'll see you next week. Thanks so much.